Formula One explained, technology and strategy. Governing question: why is Formula One widely regarded as the pinnacle of motorsport engineering from a technical and regulatory perspective? Formula One is often described as the pinnacle of motorsport engineering. The phrase is used frequently, but rarely examined in detail. It is tempting to assume that this reputation comes from speed alone. After all, Formula One cars are among the fastest circuit racing cars in the world. However, speed by itself does not explain Formula One's position. Other categories are fast. Some are faster in a straight line. Other categories of motorsport operate with fewer technical restrictions. What distinguishes Formula One is not raw performance, but how that performance is achieved. Formula One represents a unique engineering environment where advanced technology, strict regulation, and continuous optimization operate simultaneously. Performance is not discovered by freedom, but by constraint. In this episode, we will explain why Formula One occupies this position from a technical and regulatory perspective. We will examine how the rules shape the engineering challenge, why teams are forced to think in systems rather than individual components, and why success depends on disciplined decision-making rather than isolated innovation. By the end of the episode, you should have a clearer understanding of why Formula One engineering is widely regarded as uniquely demanding and why its competitive complexity is difficult to replicate elsewhere. At the heart of Formula One's engineering challenge is regulation. Every Formula One car is designed within an extensive technical rule set. These regulations define dimensions, materials, aerodynamic surfaces, power unit architecture, energy usage, and minimum weight. On the surface, this level of restriction might appear to limit innovation. In practice, it does the opposite. Rather than prescribing exact solutions, Formula One regulations define boundaries. Within those boundaries, teams are responsible for designing and manufacturing the majority of the car themselves. This creates a complex optimization problem. For example, increasing aerodynamic downforce improves cornering performance. However, it also increases drag, which affects straight-line speed. Additional downforce may require structural reinforcement, increasing weight. Weight changes influence tire behavior and braking performance. None of these factors exist in isolation. Aerodynamics cannot be separated from suspension. Suspension geometry influences ride height. Ride height affects underfloor airflow. Underfloor airflow determines downforce stability. Similarly, power unit performance cannot be considered independently. Cooling requirements influence bodywork shape. Bodywork shape affects aerodynamic efficiency. Energy recovery strategies influence how power is deployed throughout a lap. As a result, Formula One engineers are not solving individual problems. They are managing interconnected systems, where improvements in one area often introduce compromises elsewhere. This systems-based complexity is one of the defining features of Formula One engineering. The challenge is further intensified by the operating environment. Formula One cars must perform across a wide range of circuits. Some tracks prioritize high-speed efficiency. Others demand mechanical grip and traction. Some place heavy thermal loads on tires and power units. Others test braking stability and energy recovery. Environmental conditions add further variability. Temperature affects tire operating windows. Wind direction alters aerodynamic behavior. Weather changes can shift the balance between downforce, grip, and cooling. Engineers must therefore design cars that are not optimized for a single condition, but capable of performing consistently across many. In Formula One, peak performance is less valuable than repeatable performance. A car that is exceptionally fast under narrow conditions may be difficult to operate across a race weekend. A slightly slower but more stable car often delivers better overall results. This emphasis on consistency is not a philosophical choice. It is an engineering necessity. Technical excellence in Formula One cannot be separated from strategy. Regulations evolve continually. They respond to safety concerns, cost controls, sustainability targets, and competitive balance. Teams must therefore engineer with an understanding of both present and future constraints. This introduces strategic trade-offs. Resources allocated to short-term performance gains may limit flexibility when regulations change. Aggressive design concepts can deliver peak results, but may increase sensitivity to operating conditions or reliability risk. More conservative approaches may sacrifice headline performance, but allow for smoother development and adaptation over time. Because regulations restrict solutions rather than prescribing outcomes, teams often interpret the same rules differently. These interpretations become embedded in design philosophy. Over multiple seasons, those philosophical choices shape competitive trajectories. Success in Formula One is therefore not simply a function of budget, technology, or talent. It depends on decision-making under constraint. Engineering choices are inseparable from strategic judgment. Formula One is regarded as the pinnacle of motorsport engineering, not because it allows unlimited technical freedom, but because it demands exceptional performance within narrow boundaries. The challenge lies in optimization under constraint. Understanding how systems interact, managing trade-offs, and delivering consistent performance across changing conditions and evolving rules. It is this discipline, rather than speed or spectacle alone, that defines Formula One's engineering distinction. If you found this explanation useful, you can follow or subscribe to Formula One Explained. Technology and strategy for future episodes.